Here are the solutions to homework set number 12 for ECE 461 control systems. This homework set looks at Bode plots, Nichols charts, gain and leak compensation using Bode plots. Now the first problem is, given a Bode plot, what's the transfer function? Now we did that back in the time domain. In the time domain, given the step response, I can tell you where the poles are from the settling time, the overshoot. I can do the same thing in the frequency domain. The trick is to change colors. First, draw on your straight line asymptotes. Note that if I have s to the 0, the slope is 1. If I have s to the minus 1, this drops by 10 as s goes up by 10. 10 is 20 dB, so the slope is minus 20 dB per decade. So that's minus 20. S to the minus 2, 2 poles, gives you s squared, 40 dB per decade. That's 100. 100 is 40 dB in 1 decade. So I want to draw asymptotes at slopes of 0, 20, 40, 60, 80 dB per decade. So initially, it looks like here's one asymptote. It's a constant, like minus 20 dB per decade. If I go, correction, 0 dB per decade. At 20 dB per decade, so here's 1 decade, right here. Here is 20 dB, so there's minus 20 dB per decade. This is 40. Here's minus 40 dB per decade. Minus 60, minus 80. And the trick is to add these lines together, move them around until they're tangent. So like to take this guy, oops, I didn't draw that quite right. You got to get the slope right. So there's my slope. That'd go right about here. Take this slope, comes in about like this. The next slope. Where they intersect are your poles. So doing that, drawing these straight lines, I get these curves. Where they intersect is your pole. That's why it's called a corner frequency. It's a corner on your Bode plot. The corner is where the pole is. So there's a pole right here at about 0.5, another pole right here at about 2.1, another pole right there at about 5, and another pole at about 21. So this is the form of my filter. I've got poles at the corners of my Bode plot. To find k, pick any frequency you want. So the poles set the shape. What k does is it takes this curve and slides it up and down. If I have the right shape and match the point, I've matched the curve. So I'm going to pick 0.1. At 0.1 radian per second, I want the gain to be 20 dB. Or, assuming this is flat, at 0 radians per second, infinitely far left, the gain is 20 dB. Or 10. Find k to make the gain 10. So k is 1102. There's my compensator. And your answer is going to vary a little bit. Depends upon how you draw the asymptotes, where the corners line up. But it should be something kind of like that. Another problem. If you have complex poles, I get resonances. So here's kind of the same problem. I've got, here's 0 dB per decade. Here is 20 dB per decade. Here is 40 dB per decade. Which one of these kind of match up? And that's about 40 dB per decade. So I'm going to go from here, go to plus 30. There's the first asymptote. Over here, this is 0 dB per decade. Here's 20 dB per decade. Here's 40 dB per decade. The 40 matches up pretty well. And then there's another one at 0 dB per decade, right about here-ish. Kind of a trick, this peak ought to be right above that corner, just about. So kind of slide these curves around until they match up. And I get these lines. What that tells me is here's a corner. I've got 2 poles, because the slope dropped by 40 dB per decade. Gives you 2 poles at this frequency, about 0.445. I've got 2 poles at this frequency, 1098, about 8 radians per second. That tells you the magnitude. So there is 2 poles at 0.42, 2 poles at 8. To get the angles, I find the gain at the corner. This is a resonance, about 8 dB. This is about the same. The gain at the corner tells you zeta. So 1 over 2 zeta is the gain at the corner. 8 dB is 2.51. solve for zeta. Zeta is 0.199, or 78 degrees. So that is theta, and that's also phi, since they were both 8 dB. The s squared in the numerator comes from over here. This is going up at 40 dB per decade. So that tells me I've got 2 zeros to the left of 0.1. Where they are, I can't tell. It's off the graph. So I'm just going to assume 0. Infinitely far left. Finally, I've got a gain k. What I've done so far is I've gotten the right shape, but I can take the whole curve and slide it up and down by multiplying by k. Pick any frequency you want. At 0.1, the answer should be minus 12. At 2, should be 14. At 100, should be minus 30. Pick your favorite. I chose 2. It should be 14 dB. Solve for k. And I wind up that k is 290. So there's g of s. I can check if I take that g of s, plot the gain in MATLAB, I get basically the same curve. Okay, so that is given the frequency response, find the transfer function. Problem 3 is, suppose I've got the frequency response, design a gain compensator so the resonance is 1.5. Well, to do that, I will use a Nichols chart. I'm going to take this data and plot it on a Nichols chart. So here's my Nichols chart. I've got the first one. Gain is 9 dB at minus 140 degrees. So here's 9 dB at minus 140 degrees. There's my first point. 6 dB at minus 153. Here's 6 dB at minus 153. 2 dB at minus 168, and so on. That's one way to do it. On a test, that's what I would do. In MATLAB, what I can do is take these points, convert it to a complex number, g of j omega, that's 10 to the dB over 20, add an angle of e to the j, phase, in radians, gives you a complex number. Now let's do a Nichols chart with a resonance of 1.5. So here's the m sub m is 1.5. This is your g of j omega. What that tells me is that I'm stable. When the phase is 180, the gain is less than 1. So I'm stable, that's good. But the resonance is way too high. I'm going inside the M circle. To give a resonance of 1.5, I want to back off on the gain, take this curve and slide it down until I'm tangent. So what I can do on a test is kind of guess how far that slides, and that's right around 7 dB. So k is minus 7 dB. Or in MATLAB, just guess. Is it 0.5, 0.3, 0.34, 0.35? At 0.35, I'm tangent, so here k is 0.35. And in MATLAB, 0.35 is a gain of minus 9 dB. So actually this distance was minus 9 dB. I didn't read it right. That distance is about that far. 9 dB down. That's gain compensation with a Nichols chart. As a sidelight, it's the same thing if I do a Nyquist diagram. If I do a Nyquist diagram, I plot the real part of G versus complex part. My M circles are now circles rather than ovals. I want to be tangent to my M circle, so here's G, here's 0.35 times G. Same idea. Or an inverse Nyquist plot. Do an inverse Nyquist plot, here's G, here's 0.35 times G. I want to be tangent to my M circle. So pick your favorite diagram, Nyquist, inverse Nyquist, Nichols, they're really all the same. Problem 4 then is design a gain compensator for 40-degree phase margin. Then check the response in MATLAB. So what you're doing with phase margin is on a Nichols chart, I've got an M circle. I want to be tangent at this point. That point's kind of a hard point to find. So instead what I'm going to do is when the open loop gain is 0 dB, find this point right there. Hit the M circle when the open loop gain is 0 dB. And this is the point that I really want, hard to find. This point's easy to find. The 2 points are almost the same, usually. So designing for phase margin is about the same as designing for resonance. That's the idea. So I want to design for a 40-degree phase margin. So that's actually pretty easy. I just search at what frequency is the phase shift 40 degrees away from 180, meaning minus 140 degrees. That frequency is 1.71 radians per second. Found using numerical methods. Just guess, guess again, guess again. At that frequency, the gain is 0.5. I want the gain to be 1, so K is 1.95. Same thing we did in root locus. At your design point, make the gain 1. Here, the design point is at what frequency is the phase minus 140. What that should do is the resonance then is roughly G over 1 plus G. Assuming this is my resonance, the resonance is 1.46. That gives you a damping ratio of 0.36, gives you 28% overshoot. So a 40-degree phase margin is the same thing as 28% overshoot. Different way of saying the same thing. The closed-loop dominant pole is the resonance is at 1.7 radians per second. That's the complex part of the pole. The real part gives you the damping ratio of 0.36. So the real part is 0.67, 5.89 radians per second. Kind of what you're doing is the resonance is right here. That's the complex part of the pole. That is 1.71 radians per second. The phase margin tells you resonance. Resonance tells you zeta. Zeta tells you the angle. If I know the complex part and the angle, I can tell you the real part. The real part's 0.67 or 5.89 second settling time. Checking MATLAB, here's G, here's K. Closed loop system, take the step response. I should have 28% overshoot. It's actually 30%. That's typical when you design for phase margin. I intersect the M circle, meaning the resonance is too high, meaning the overshoot is too high. Close, but a little bit high. The settling time is about 5.8 seconds. No error per step input. Kind of what I expected. Now design a lead compensator. So I'm going to take a shortcut. Here's the pole that's causing trouble. Put the 0 to cancel that pole. What I could also do is 1 to 3 times my resonance. My resonance was 1.7 radians per second. So put the 0, 1 to 3 times 1.7. 3 is in that range, so that works. Now here's G times K. Now find the frequency where the phase is minus 140. That's now 3.7 radians per second. Make the gain 1 there. K is 42. So there's K of S. The closed loop system should have the same overshoot. It's the same phase margin, meaning same zeta, meaning same overshoot. The settling time should be faster. This corner is 3.78 over 1.7. That much faster. So the settling time should be that much slower, that much quicker. Or I can say, here's the pole, here's the complex part. That's my resonance. The real part is 1.49. Settling time is 2.67 seconds. Taking the step response, the closed loop system in MATLAB, here's G, K, closed loop system. It's a faster system, quicker settling time, still about 20% overshoot, a little bit higher, because again I designed for phase margin. That tends to give you slightly too much overshoot. Problem 6. Suppose I add a delay. That's this guy right here. The beauty of frequency domain is I don't have a problem with delays. As long as I can tell you the phase and the gain, I have no problem. Same as before. Now search where is the phase of G of S minus 140 degrees. That's at 1.2 radians per second. Make the gain 1. There's K. Plotting the closed loop system, here's your G. There's my delay. I'm going to use a 6th order Bode approximation. Form the closed loop system, G times delay times K over 1 plus G times delay times K. Plot the step response. I now have 32% overshoot. Should be 28%. It's close. And your step response. Okay, note, delays are not a problem when designing in the frequency domain. If I want to have a lead compensator, I'm going to pick the 0 to be 1 to 3 times 1.2 radians per second, or cancel the pole at minus 3, just like before. Either way works. Here's your closed loop system, or open loop system, G times K. Now find the frequency where the phase is minus 140, 1.99 radians per second. Pick K to make the gain 1. There's K of S. Check the closed loop system in MATLAB. GK over 1 plus GK with a delay, and I have 34% overshoot. So again, kind of note, in the frequency domain, I don't really need the transfer function. I can design using a Nichols chart. All I need is gain versus frequency. In the frequency domain, I don't really care about delays. They're not a problem. I can just find the gain and phase shift of a delay. Not an issue. And the results are pretty similar to what we did in the root locus plots. If I had a lead compensator, I typically pick the lead compensator to cancel the slowest stable pole, stick it out of harm's way, like 10 times further out, and then adjust the gain. But now I adjust the gain to set the phase margin rather than the damping ratio. But phase margin is resonance, is damping ratio, different way of doing the same thing. That is homework set number 12 for ECE 461.